So in interface, we will create two clocking blocks. Okay. So one clocking block is for driver, another clocking block is for monitor. Okay. So here, if you observe clocking, driver CB is the name of the clocking block. You can take any name, user defined at the rate of negative edge of the clock, either negative edge of the clock or positive edge of the clock, that your wish according to the specification. Okay. And default input skew. So what is mean by skew? So if you observe here, skew is in the sense, if an input skew is specified, then the signal is sampled at the skew time units before the clock event. So what is the input skew? At the positive edge of the clock, the before positive edge of the clock, that half part is input skew. After positive edge of the clock, remaining part, half part is a output. Okay. So mainly at that particular time, if output skew is specified, then output signals are driven skew time units after the corresponding clock event. So a skew must be a constant expression and can be specified as a parameter. Okay. So like this, we'll write the skew. Default input 10 nanoseconds or 20 output is 2 nanosecond. So at what time it should be sample the data. So that depends on the skew. So if you observe same, we have written here default input 1 output. And another thing is here, if you observe, all the signals, input signals are declared as a output and output signals are declared as a input. And in the monitor clocking block, all the signals are declared as a input. Why? Because suppose here is the driver and here is the monitor. From driver, we are getting the data from the mailbox, the input data. So the inputs, whatever the inputs are there, those are the output to the DUT. Those are the output to the DUT. And from the driver, we won't send any output data to the DUT. We will randomize the input data. That input data only we send to the DUT. So all inputs should be declared as outputs. And from the DUT, all input and output data will get to the monitor, right? So that's why all signals are declared as a input to the monitor. Okay, so some other example if you consider here. This is another example for the clocking block. So here in the clocking block driver CB, all inputs are declared as output, and sometimes and most of the times no need to declare the inputs in the driver clocking block. And here in the monitor clocking block, all the inputs are declared, all the variables are declared as an input because all the signals are getting from the DUT to the monitor. That's why. Okay. So this is the signal connection. So whenever you want to pass the data to the DUT, you will access this path. Okay, the clocking block, clocking path, like the term mod port. So how we will write the mod port? Mod port driver, clocking driver CB, input lock, comma input reset. Okay. Otherwise, this is another model. We can directly put the clocking block driver CB because already all the inputs are mentioned in the clocking blocks, right? So no need to mention in the monitor again, mod port again. Okay. If you don't want to write like this, you need to write all these inputs and outputs again in the mod port block. Without writing like that, we are just putting the clocking driver CB. Okay. Did you understood up to here? Like monitor also same. Have you understood up to here? So now how we are accessing all the signals from the driver? If you go driver, so created the virtual interface. If you see second line, that is the macro. Okay, tick defined macro. So how we are accessing each signal? If you observe here, the transaction data. So tr1 dot request data in tr dot request command in tr dot tag data, all the data we are sending to the DUT. So how we are sending to the DUT? Through this path. We already set the path here. If you observe, for this macro, driv if is the name of the macro, cal if is the name of the virtual interface, dot driver is the mode port name. So if you observe here, driver is the mode port name, driver cb is the clocking block name. Okay, so cal if dot driver dot driver cb dot these signals. So we are accessing these interface signals in the driver through the virtual interface. Okay, you can set the path in this way by using the macro, by using the tick define. Otherwise, another way of coding method is, if you observe here, drif is the name of the virtual interface, dot drcb is the name of the clocking block. See, grcb is the name of the clocking block of the interface here, and drif is the name of the virtual interface. Dot request one command in, request two command in, we are sending the data to the DUT. Okay, so these are the different ways of coding practice. So whenever you are practicing on more examples, then you will get this coding style. Okay. Now, have you understood what is the difference between virtual interface and interface? Everyone? Is it little bit confusion?
Yes, ma'am.
Okay. So, I will share the link. Okay. So, go through the transaction class, understand the interface, and try to understand overall this driver code. Okay. Overall, in the sense, just try to understand the virtual interface. This one. Okay. That two will be enough, and how we are sending the data. Okay, that would be the assignment for tomorrow. Okay, try to understand up to this. Is there any doubts still up to here? Once you completed with up to virtual interface, we'll move to the OOPS concepts. So
Okay,
virtual
ma'am.
interface is the main now. So the virtual interface OOPS concepts. Okay, but very clear, be clear up to the virtual interface, everyone. Okay. Any doubts? I will share you those codes. Don't go through very deep into the design, test bench and all. Just go through the interface, transaction class, generator class, driver class. Okay.
Okay, ma'am. Ma'am, in SystemVerilog, the test bench is messy and some kind of complicated. That's why we are moving for the UVM.
Sorry, SystemVerilog.
SystemVerilog, that test bench,
Mm.
it is kind of complicated, right?
Yes,
So many classes we have to declare and all.
yes.
So, so that's why we are moving for the UVM.
No, no, no. UVM is very complex than SystemVerilog. But why we are moving to the UVM means, suppose if you see, if you want to create the generator here, everything we need to declare from, everything we need to write from the scratch. Okay. If you want to generate a driver or monitor, everything we need to write the code from the scratch. But in UVM, what happens means everything is a library. Okay, So if you want to write any code for generator, means by default generator logic will be there in the UVM. By default driver logic will be there in the UVM. So everything will be mentioned predefinedly. Everything is mentioned in the UVM. So easily we can access. Okay. Suppose a simple example. Suppose if you want to verify the same design using the Verilog HDL, how many days it will take? Suppose all scenarios if you want to verify, maybe it will take 6 months time for a simple design in Verilog HDL. Okay. By using the system Verilog, we can verify easily in 3 months. Like that in UVM, if you take in 1 month, we can verify the entire design. Okay. So there are it have so many good topics compared to system Verilog. Whatever the limitations are there here. So based on that limitations in UVM, there are some advanced topics. Okay. So that's why that is complex only, not very simple.
Okay, ma'am.
Yeah. So based on Verilog, what are the limitations are there? Like it doesn't have any based verification. It doesn't have proper randomization, and we cannot do any coverage analysis. So these are so many limitations. So those are covering in the system Verilog. Like that system Verilog also have different limitations. Those are covering in the UVM. So that's it. Okay.
Okay, ma'am.
Yeah. Okay, then everyone, please go through up to interface. Okay, please revise all the concepts, and coding is very important. Okay, so you must be in a stage, you must be develop your own verification plan by end of the project. Okay, so please do practice. Okay, okay then. Okay then, thank you all.
Yeah, ma'am. Thank you.
I will share the codes. Please practice. Okay.
Okay, ma'am.
Yeah. Okay.